Welcome to the Deep Dive, where we take a deep dive into some fascinating topics. And today it's all about secure communication.
Yeah.
I mean, think about it. Like every time you send a private message or buy something online, the security of that exchange, that's super important, right?
It really is. I mean, in today's world, keeping those digital interactions private is, it's paramount. And when we talk about that kind of true privacy, especially with end-to-end encryption, well, RSA encryption is often the technology behind it all. It's a real cornerstone, making sure that our data stays safe and sound.
Yeah, RSA. I feel like everyone's heard that term, but I'll be honest, I don't think everyone really knows how it works. So that's what we're going to do today, peel back the layers, figure out the magic behind it. And, what I'm really interested in is how does RSA protect your info, even if, and knock on wood, you lose your phone, right? Your phone gets stolen, all your data's on there. Is that stuff still safe? We're going to find out. Our guide for this deep dive is the N5 digital paper end-to-end RSA encrypted communication .pdf. It's a great resource. So to kick things off, what is RSA? What makes it so special?
Well, at its heart, RSA uses this really clever mathematical trick. It's simple to do one way, but super hard to reverse. Kind of like, when you mix two colors of paint together, it's easy to mix them, but almost impossible to separate them again, right? That's kind of the idea here. It's easy to do in one direction, but really tough to undo. And with RSA, that's multiplying two huge prime numbers. Easy for a computer, but try taking that huge result and figuring out the original two primes. That's a whole different ballgame. It's a massive challenge.
Like a one-way street for math, huh?
Exactly. A one-way street. And that's the whole basis for RSA security.
I see. And so this one-way street, it does more than just scramble messages, right? I mean, it provides some pretty crucial things for secure communication in general, doesn't it?
Yeah, you got it. RSA gives you three really powerful things. First, you have that secure encryption, turning readable data into, essentially gibberish that only the intended person can understand. Then you have digital signatures. Think of them like tamper-proof seals. They verify the sender and make sure nothing in the message has been changed. And the third thing, secure key exchange. You don't have to meet in person to exchange keys, which is, it's kind of revolutionary for online stuff, isn't it?
Totally. Okay. So how do we get started with this whole system? Where do these keys come from? What I found really interesting in the paper was that you, the user, you're the one generating these keys. It's not like some big authority handing them out.
That's a really important point. Yeah. It's all about user control. When you, let's say, set up a secure messaging app or some other encrypted service, it's your device right there in your hand that creates your unique RSA key pair. And it does this using some very sophisticated cryptographic libraries that are built right into the software.
Okay, so let's dig into this key creation process. How do these apps on our phones make these mathematical secrets? How do they work?
It all starts with generating those big, and I mean big, prime numbers. We talked about those before. In standard RSA, you usually have two of them. We call them P and Q. The paper does mention multi-prime RSA, which uses, you guessed it, more than two primes, but they're right, it's not as common in everyday software. The security here, it hinges on just how huge these prime numbers are. Like hundreds of digits long, that kind of huge.
Whoa. Finding numbers that big and then making sure they're prime.
Yeah.
That's got to be like finding, a specific grain of sand on every beach in the world. How do our devices do that?
Well, they use what we call CSPRNGs, cryptographically secure random number generators. It's a mouthful, I know. But think of them like super fancy dice rollers. They spit out these strings of numbers that are basically impossible to predict. Once they find a number that might be prime, they put it through some intense testing, primality tests. The Miller-Rabin test and Fermat's test are mentioned in the paper, and they're like really accurate filters, making sure with a high probability that the number is truly prime.
So once we have these massive prime numbers, what happens next? The paper mentions this and in the fee. What are those all about?
Right. Those are the next ingredients. And this step is actually pretty simple math-wise. You just multiply those two primes, P and Q, together. And the answer you get, that's N, which is called the modulus. This N is public. It's part of both your public and private keys. Now, we also need to calculate something called the totient. It's represented by the Greek letter phi, so fidin. When you've got two primes, it's easy to calculate, just P1 multiplied by Q1. It might seem a bit abstract right now, but trust me, this phi-init is working hard behind the scenes, making sure that the encryption and decryption processes work the way they should.
So we're building this mathematical framework step by step. We've got the primes, we multiply them to get n, and then we got phi, and what's next?
Okay, so now we need to pick something called the public exponent. It's usually written as E. Now, E has to follow a couple of rules. It has to be co-prime to feen. Think of it like two gears that don't quite mesh. Their only common factor is 1. And it has to be a number between 1 and feen. Often 65537 is used for E because it's a prime number, and it strikes a good balance between security and speed.
Okay, and then we get to this super secret part, the private exponent D. This is the one we got to keep safe from.
Absolutely. This D is mathematically tied to E and fine. Basically, if you multiply D by E and then divide by fine, the remainder has got to be 1. Think of D as the key that unlocks the encryption done by E. It's calculated using some fancy algorithms. And this deed, it's what lets you undo the encryption and get back to the original message.
Okay, so let me see if I've got this straight. The public key, that's the pair ICANN, and you can share that. It's like giving someone your address, your digital address. But the private key, that's DNETN, you keep that super secret, like the actual key to your house.
You got it. And the whole security of RSA, it all comes down to keeping that SATA secret. Even if someone knows your public key, EAN, it's just about impossible to figure out from that info. That's what makes RSA so secure. Oh, and the paper mentions some of the big players, the cryptographic libraries that do all this heavy lifting for us. OpenSSL, Bouncy Castle, libsodium, these are the trusted tools that apps use behind the scenes. And because your device generates these keys, you end up with a totally unique pair that no one else has. Pretty neat, huh?
Yeah, it's good to know it's not some mysterious process, that there are these established and tested tools being used. Okay, so we've got our keys, public and private. But how does an actual message, like something I type on my phone, how does that get turned into all these numbers that RSA can use?
That's the next step. Remember, RSA works with the numbers, so anything text message, photo, video, whatever, it all has to be turned into numbers first. Got to speak the language of RSA, you know.
Okay, so let's start simple. Text message. How does that become a number that RSA can work with?
So when you type a message, each character, each letter, number, symbol, it gets turned into a sequence of bytes using an encoding system. UTF-8 is a common one. Think of it like each character has its own unique numerical code. Then, that whole sequence of bytes, it's treated as one giant integer, one big number, like taking a bunch of digits and sticking them all together.
And what about those photos and videos we send? Those are way bigger than a text message. How do those get turned into numbers?
It's the same idea, really, but with a lot more data. The file, it's read as raw binary data, which is basically a long string of zeros and ones. That binary data gets converted directly into a single integer. Programmers use functions like int.from.bytes for this. It just takes those bytes and turns them into one big number.
Okay, that makes sense for turning data into numbers. But encrypting those potentially massive numbers with RSA, that seems like it would take forever, especially for big files, right? Like a whole movie or something.
You're right, that's a good point. Encrypting huge amounts of data directly with RSA would be really slow, it'd eat up your battery, and that's why we use this really clever thing called hybrid encryption. The paper talks about this. It's all about efficiency.
So how does this hybrid approach work? How does it use RSA with other encryption methods to handle these bigger files?
It's all about combining the strengths of both asymmetric encryption, like RSA, and symmetric encryption, like AES. Symmetric encryption is much faster for big chunks of data. So first, we generate a random secret AES key. Then we encrypt the actual content, like your movie file, using that AES key. After that, we take that AES key, which is pretty small, and we encrypt it using the recipient's RSA public key. And finally, we send both the RSA encrypted AES key and the AES encrypted data to the recipient. On their end, they use their RSA private key to decrypt the AES key, and then they use that decrypted AES key to quickly decrypt the big file.
That's smart. It's like using a super fast lock for the data itself, and then using a slower but way more secure lock to protect the key to that first lock. Okay, so we get how messages turn into numbers and how they're encrypted, sometimes with this cool hybrid method. But how does it actually work when two people are having a conversation, sending messages back and forth?
Right, so it all starts with a key exchange. Like we talked about before, everyone generates their own public and private key pair. Then they share their public keys. This usually happens automatically in the background through the app servers or directly between devices. The important thing is Alice has Bob's public key and Bob has Alice's, but they each keep their private keys totally secret. Got it.
Got it. So Alice wants to send Bob a message. She takes Bob's public key, turns her message into a number, maybe using that hybrid encryption method we discussed, and then she does that RSA encryption using his public key, and the formula C mod and M is the message is a number. He's is Bob's public exponent, and N is his modulus. And what she gets C, that's the encrypted message.
Perfect. Bob receives that encrypted message, C, and his device takes over. It uses his private key, DAN, to decrypt the message using the formula M equals CD mod N, where D is his private exponent and N is his modulus. This math, it perfectly reverses the encryption, and voila, Bob can read Alice's message.
And for Bob to reply to Alice, we just flip it around. Bob encrypts his message using Alice's public key, and Alice decrypts it with her private key.
Exactly. Back and forth, all based on the secrecy of their private keys. As long as those stay secret, the conversation is safe.
Let's try to explain those encryption and decryption formulas in really simple terms, just so anyone who's not a math whiz can understand.
All right, so imagine this. Your message becomes a number. Then you take that number and raise it to a certain power. That's E, the public exponent. You divide the result by another number, that's N, the modulus, and the leftover you get, that's your encrypted message. Makes sense.
And decryption is like doing the opposite to get back the original message.
Right. You got it. You take the encrypted number, raise it to a different power, that's your private exponent, and divide it by the same N, the modulus. The leftover this time is the original message. The cool thing about RSA is how those specific numbers, E and N, are all connected, so this works out perfectly.
It's pretty amazing how this math keeps our conversations private. Now, the paper says that the difficulty of factoring that modulus in back into its original prime numbers, that's super important for RSA security.
You bet it is. The whole security of RSA relies on how hard it is to take in and figure out the original primes P and Q that were multiplied to make it. If someone found a quick and easy way to do that, they could crack the code, they could get the private key then from the public E and N, and then, well, the whole system would be vulnerable.
And that's why the size of these keys, measured in bits, is so important, right? The bigger the key, the bigger the N, and the harder it is to factor.
Exactly. The paper recommends at least 2048 bits for the key size for decent security these days, and bigger keys like 3072 or 4096 bits offer even more protection against people with powerful computers trying to crack the code.
Beyond the math and the key size, what are the most important things for people to do to stay safe when they're using RSA encryption?
The number one thing, no question, keep your private key safe. If someone gets a hold of your private key, they could potentially decrypt all your messages, past and future. That's why the paper really emphasizes using hybrid encryption for big files. Even if the RSA part was somehow broken in the future, the data itself would still be safe because of that AES encryption. And of course, always use trusted cryptographic libraries, the ones made by reputable developers. That helps avoid any weaknesses in how RSA is put into practice.
This brings us to a really crucial part of the conversation, and our source material dedicates a whole section to it. How are these private keys actually stored on our devices, and how does that storage protect us if our phone or computer disappears? It's the section on private key storage and protection, and I think it's something everyone should understand.
It is. It's fundamental. Understanding how your devices protect that private key, that's key to understanding the whole power of end-to-end encryption. The paper explains that an RSA private key is more than just that EAD value. It's got the modulus N, and sometimes it includes the original primes, P and Q, and even other values used to make things faster. These keys are often stored in certain file formats. PEM is a common one. It's text-based. And DER, that's another one. It's binary.
And this storage, it's different depending on what device you're using, right? Phone, tablet, computer.
Exactly. On iPhones, for example, those private keys are usually kept in the secure enclave or the keychain. And here's the important thing, like the paper points out. Those keys are usually non-exportable. That means even if someone got into your phone's software, they couldn't just grab the private key. It's locked away in a special hardware-protected part of the phone, super hard to get to.
That sounds really peculiar. What about Android phones? Do they have something similar?
Yep, they sure do. Android has something called the Android Key Store, and the paper mentions that on many new Android devices, this key store is also hardware-backed, just like the secure enclave on iPhones. That hardware backing, it adds a whole other level of security, and the keys stored there are typically non-exportable as well, so even if you lose your phone, the private key stays protected inside that secure hardware. Pretty impressive, right?
So on both iPhone and Android, they've got this system where the private key is locked down in the device's secure hardware. What about laptops and desktops? The paper makes it sound like things are a bit different there.
Yeah, you're right. On desktops, private keys are often stored as files on the hard drive. They usually use that PEM format we talked about earlier. And the best practice here is to make sure those files are encrypted. We use strong encryption algorithms like AES, and the key for that encryption comes from a strong password that the user creates. The paper also talks about HSMs, hardware security modules. Those are special devices made specifically for storing cryptographic keys. Unlike phones, where keys are often non-exportable, keys on desktops sometimes can be exported, but that's risky and should only be done if it's absolutely necessary.
So the paper really hammers home this idea of encrypted key storage. And I get why. Like it says, if your private key isn't encrypted and your device gets hacked or stolen, all your encrypted messages could be exposed. That's a big deal.
No doubt about it, that's a vulnerability you want to avoid. But the flip side, and this is what I find so cool, is how strong those secure enclaves and keychains are on smartphones. Because those keys are usually non-exportable and protected by that separate hardware, even if someone steals your phone, they can't just take the private key and decrypt your messages. It's still safe. That's powerful. It gives people a lot of peace of mind.
It really does. So to sum it all up, we've covered a lot about RSA encryption. The math behind the keys, how messages become numbers, how encryption and decryption work, and, most importantly, how those private keys are kept safe on our devices. Especially that non-exportable thing on phones. That's a big deal.
Totally. RSA is a solid, widely used system for secure digital communication. It lets us create these unique digital identities with key pairs, scramble and unscramble messages. And it can even handle big files efficiently with hybrid encryption. And like we said, the security of it all depends on how well we manage and protect those private keys. That's the heart of it all.
And that last part about the private key storage, that's what I find so reassuring. Even if you lose your phone, the way these systems are designed means that your private data, it's still locked up tight. It's like having a digital safe that no one can break into.
Exactly. It's pretty incredible when you think about it. We have these digital vaults on our phones, and this sophisticated cryptography is working all the time to keep our digital lives private. It makes you think about the big picture, about how important this secure key storage is for our security and privacy in a world where we're all so connected.
It really does. Well, that's about all the time we have for today's deep dive. But, keep thinking about those digital vaults and all that invisible cryptography working hard to protect your data. It's a fascinating world out there.
It really is. Stay curious and stay safe out there.
Thanks for joining us on the deep dive. We'll see you next time.